Hi, my name is Christopher Hyatt, and this is my Circuits Lab. As a brief introduction, the general purpose of this lab is to explore how circuits react under different conditions using a PhET simulation. Some fundamental physical principles that will be involved in this lab are conventional current, resistors, capacitors, current, and batteries in circuits, as well as potential differences. The final result will show that resistors and capacitors and batteries all affect conventional current and can be measured through potential difference and ammeters, which measure the current specifically. Models to be used include images of the circuits, a graph of potential difference, and a graph of the natural log of the potential difference versus potential difference not versus time, which will become relevant later. Next, we will hop into the experiment section. Here we see the first circuit, where the system is the entire universe and there are no surroundings, because there's no relevant interchange between systems and surroundings, which will hold true for all of the circuits. The initial conditions are there's no current flowing, and then we attach the battery, and everything is zero, and then almost instantaneously we see the circuit, the current that is in the image, and that will also hold true for the rest of the images. The predicted current that I obtained mathematically for this circuit was 0.0204, and then the simulated was 0.02, so that held constant. And then a little question is, what would happen if we reversed an ammeter? It doesn't actually work in the simulation, but hypothetically, if you were to reverse one in real life, it would show a negative reading instead of a positive. When we replace an ammeter with a voltmeter, we can see that the potential difference between these two sections of the circuit is 3 volts, and then there's no current running through the circuit. This is because we've detached a piece of the circuit and the circuit is no longer complete. And then here we see that the current is back to 0.02 amperes. And we measured the potential difference among each section of the circuit, which we'll see in the next slide. And the reason the voltmeter does not affect the flow of the circuit is because the voltmeter prongs thing have very, very high resistance, so the current does not flow through them any more than necessary to detect the voltage, which is the same reason the current couldn't flow in the previous slide. Here we see a graph of potential difference versus position as measured using the voltmeter. You can pause here if necessary. Here we replace the voltmeter with an ammeter, and we see that the current changes from the previous readings to 0.06, and that's because the electricity has been given a path of less resistance to flow down, which increased the current, or increased the amount of current able to flow through the circuit at once. Next, we have the calculated R values using the previous graphs and values, and we find that the 47 ohm resistor has an R value of 47 ohms, the 100 ohm resistor has a value of 100 ohms, the wires have a resistance of 0 ohms in this idealized situation. This would not hold true in real life. And the ammeter has a resistance of 0 ohms, which is also idealized and would not happen in real life. Next, we're going to add a capacitor and analyze the behavior of the capacitor. Here we see what happens when we add a capacitor. We can see the capacitor building up charge, and as it builds up charge, the current flowing through the wire decreases, as seen through the decreasing brightness of the light, until it eventually goes out. The time that it took the capacitor charge with a 10 ohm resistance bulb, a 0.2 farad capacitor, and a 9 volt battery was 6.24 seconds measured, and the discharge time was 6.69 seconds. When we replaced the light bulb with a 20 ohm bulb, the time to charge was 11.66 seconds, and the discharge time was 11.79 seconds. Using the same setup but with a 30 ohm resisting light bulb, we can plot this graph, and the slope is -1 divided by RC, giving us a measured RC of 6.09, while the theoretical RC is 6. There's a bit of error here because of the time measurements made by me. If this experiment was done in real life, using an actual ammeter and wires, there would be resistance along the ammeter and wire, and so the current would be lower. When charging a real capacitor with no resistor, the capacitor charges very, very quickly, and it would happen the same in real life, just slightly slower than if idealized. In conclusion, ammeters, voltmeters, capacitors, batteries, and resistors are all very useful tools which can help you alter or read the flow of a current in a measurable way.